Starting.
Yeah, please. Can I start?
Yes, we are live now.
Okay, thank you. So greetings from CSR Nest, Jorat, Assam. A very good morning to all of you. We are into day 4 of the International Virtual Workshop on Global Seismology and Tectonics. I would like to thank each and everyone present with us today for your continued support and participation. If you could not attend the previous lectures, the entire lecture sessions have been recorded and uploaded in the official YouTube channel of our institute, that is CSR SRTP. We are glad to have with us Professor Ramesh Singh from Chapman University, USA, Professor J.R. Kyle, Session Chairperson, and Dr. Saurabh Borua, Chief Scientist as Co-Session Chairperson. The keynote speaker of today's lecture is Dr. Nicholas Vander Elst. He's a young and dynamic geophysicist from USGS. The title of his lecture is Forecasting Aftershocks with the Epidemic-type Model. Now may I request our session chairperson, Professor J.R. Kyle, to say a few words. Over to Professor J.R. Kyle.
Oh, well, thank you very much, Antanu. I think it is going very well, Professor Nicholas. It is 4th day today, and we had many good lectures, and today also you are waiting, look forward to your listening to your wonderful lecture on forecast of aftershocks. That is, I think, very exciting topic for all of us, for all seismologists in particular. So I think without taking much time, I think I would request Professor Nicholas to go ahead. But before that, I think Santanu has got some formality to introduce you. So let you be introduced, and we all look forward to listening to you.
Yes.
Yeah.
Thank you, sir. So may I request Professor Ramesh Singh to say a few words, sir? Over to Professor Ramesh Singh.
Me? Okay. So, greetings from California. Nicholas is working with the USGS, and I'm with the Chapman University since 2009. And I was at IIT Kanpur for 23 years. Okay. So I'm very happy that I'm attending this workshop. I attended the second lecture. Okay. Whose lecture was that?
Walter.
Yes, Walter Mooney. Okay, Walter is a good friend of mine. Okay. And Walter Mooney, and it was very interesting. I'm very happy, and thanks to National Institute of Seismology, Jorhat, you people are doing great job. Okay, so I will be presenting my talk tomorrow. Okay, thank you.
Thank you, sir. May I now request our co-session chairperson, Dr. Saurabh Borua, to give his initial remarks. About Saurabh Borua.
Yeah, good morning, Professor Nicholas Vander from USGS, Professor Kayal, Professor Singh, and of course, the convener Santanu Borua. Today's lecture, Forecasting Aftershocks with the Epidemic-type Model. The thing is that this corona pandemic is going on. We had some studies to predict some of the curves, and it has been observed that it is an exponential curve. So it will be really a great deal of for us to listen to Professor Nicholas to this status, and we had already had the opportunity to hear 3 great specs of earthquake seismology, that is exactly on completeness of database, which is the very basis of any kind of prediction, any kind of modeling. And then what is happening in subduction zone near Java, Sumatra in Sulawesi earthquake. And of course, yesterday's lecture was on the ductile brittle deformation, how it is observed from the field investigations. So we are really eager to listen to Professor Nicholas, and I, on behalf of our director, Dr. G. Narahari Sastry and NIST Jorhat, thank you very much for accepting our kind invitation to deliver this lecture. Over to Dr. Santanu Borua. Thank you.
Thank you very much, sir, for your initial remarks. Now, may I read out the short biodata of Dr. Nicholas Vander Elst. He is presently associated as research geophysicist with USGS Science Center, Pasadena, California. His prime expertise includes ground-based LiDAR mapping, earthquake forecast, earthquake faults, rheology, amongst others. Prior to his present engagement, he has served as USGS Mendenhall Research Fellow from 2015 to 2018 at USGS, NSF EAR Postdoctoral Research Fellow at Lamont Doherty Art Observatory, NSF EAR Postdoctoral Research Fellow at University of California, and seismologist at Pacific Gas and Electric Company, San Francisco. He pursued and completed his PhD in Art and Planetary Science from the prestigious University of California in the year 2012. Within such short period of time, Dr. Nicholas has authored more than 24 papers. He is actively serving as an associate editor of Bulletin of Seismological Society of America since 2016. He was a recipient of USGS Earthquake Science Center Star Award for 2 consecutive years during 2017 and 2018. He was a recipient of several acclaimed fellowships such as ARCS Foundation Fellowship, NSF Graduate Research Fellowship, Chancellor's Fellowship of University of California, etc. I conclude here and request Dr. Nicholas to take the digital space and enlighten us with your lecture. Thank you. Over to Dr. Nicholas.
All right, thank you for the very kind introduction. Let me just share my screen. All right, let me try that again. Okay, here we go. All right, yes. So yeah, thank you again for that wonderful introduction. So today I'm going to be talking about aftershock forecasting with the epidemic model, which has it's gotten a lot easier to talk about the epidemic type model during the epidemic. So I want to start out, so talking about aftershock forecasting, I think the first question that people have is how does forecasting differ from prediction? Earthquake prediction is a term that I think we're all very familiar with. And so I want to spend the first part of the talk talking about the difference between prediction and forecasting. And then I'll go through and talk about the statistical models that we use to do forecasting. And then at the very end, I'll provide a very brief demonstration of some software that the USGS has developed to streamline the process of generating aftershock forecasts. And it's a very useful tool. Anybody can download it and use it to issue forecasts in their own area of interest. But to start with, I wanted to ask that question, are earthquakes predictable? And this has kind of been the holy grail for earthquake seismologists for a long time. And I think in the 1970s and 1980s, there was actually a lot of optimism about our ability to be able to predict earthquakes, to be able to say with certainty when an earthquake was coming. And there were a number of prediction experiments in the 70s and 80s, and perhaps the most famous one, at least the most famous in my part of the world, is the Parkfield prediction experiment. So Parkfield is a town that lies right on top of the San Andreas Fault in California. And it has this unusual earthquake history where it's had magnitude 6 earthquakes with very regular recurrence periods going back all the way to 1857. So since 1857, these magnitude 6s have just gone off every 25 to 30 years with great regularity. And this led seismologists in 1985 to go ahead and issue a prediction for 1988, where that long-term trend line would intersect with the next earthquake occurrence. And so what happened in that prediction experiment? So the justification for this experiment, or for this prediction, is Reed's theory of elastic rebound. I mean, this is why we think that earthquakes should be predictable, because we know how earthquakes work. And it's basically you have an unstrained crust, and then that crust is deformed by tectonic motion. It's stressed to its elastic limit. And then you have an earthquake that relieves the stress, resets the clock, and then you begin loading again. So if you think about stress versus time, you've got slow tectonic loading. It hits some strength thresholds. You've got a drop in the stress during the earthquake, and then it resets the clock. And so this really seemed like a place where we were seeing elastic rebound in action. And so we had some confidence that we could anticipate the occurrence of the next earthquake. So seismologists built a fault observatory there to capture the earthquake when it returned. So they put out GPS instruments, borehole seismometers, strain meters, creep meters, magnetometers, all of the instruments that we could think of and put in the ground to catch the next earthquake. And then we waited and we waited and we waited, and 1988 came and it went. And eventually, finally, in 2004, the earthquake happened. Oh, I'm sorry, that's the wrong picture. There we go. 2004, 16 years late, the earthquake finally happened. So even in this location where earthquakes occurred with extreme regularity, it turned out that the prediction experiment failed. And so what went wrong with this prediction? Well, if you look at this elastic rebound model, we think that this is the right way to think about earthquakes. But what we've learned as we've made more measurements and kind of learned more about faults is that this picture is just way too simple. So none of the elements in this model are constant. So the elastic rebound picture is a lot more complicated. First of all, the loading isn't constant. It's affected by transients in the tectonic motions. It's affected by faults earthquakes on nearby faults that change the loading rate on your fault of interest. The strength threshold isn't necessarily constant. Every time you have an earthquake, it resets the strength for the next earthquake. And of course, the stress drop in earthquakes isn't constant. So even though we understand the elastic model for how earthquakes are generated, we just don't have enough information about the fault zone and the pre-existing stresses to really make deterministic predictions about when an earthquake is going to happen. So this brings us to earthquake forecasting. So I like to think of there being different levels of earthquake prediction. So when I use the word prediction, I'm talking about a very accurate, precise statement about the location, size, and timing of an earthquake with sufficient precision to allow something like evacuation. Whereas earthquake forecasting is using statistics to determine when earthquakes are more likely than usual. And then sort of on this vertical scale is how specific the forecast is, so kind of how useful it is. And then on the other axis is how reliable it is. So earthquake forecasting is kind of in the middle, where you have true prediction on one end, and then you have the long-term hazard, which is just average recurrence times of large earthquakes. You measure the faults, you do the geology to figure out the average recurrence time, and then you get a sense of your likelihood of experiencing a bad earthquake sometime in your lifetime. But in the middle, which is it's good for building buildings, but it's not useful for making plans. Earthquake forecasting is in the middle, where it's not totally specific. You can't be certain, but it gives you more information than just that long-term kind of understanding that you live in an earthquake-prone country. So this is what we're going to focus on here. So an aftershock forecast is a statement about the probability of further earthquakes in a specified magnitude range over a specified time interval. Rather than saying a specific magnitude, specific time, it's just the probability over a range of magnitudes and a range of times. So it's a statement about what might happen, not what will happen. And forecasts are based on the average behavior seen in past aftershock sequences. We don't use anything like earthquake precursors, radon gas, or weird animal behavior. The forecasts are just based on average statistics of past aftershock sequences. And then foreshocks get updated as time passes and the hazard changes. So the United States Geological Survey currently issues aftershock forecasts for any earthquake larger than magnitude 5 in the United States. And we've also developed software to streamline the process of analyzing and forecasting aftershock sequences anywhere. And so I've been going around trying to promote this model and train people on this model in various countries like Myanmar, Nepal, Colombia. I'm hoping to visit more countries in the future. This is a great opportunity to show the software to a new audience. So I guess a basic question, what are aftershocks? What are we talking about forecasting here? So we're talking about aftershock forecasting, not earthquake forecasting in general. And that's because aftershocks are a lot easier to forecast than the first big surprise main shock. So aftershocks are any earthquake that occurs in a cluster or a sequence where those earthquakes are caused or triggered by an earlier earthquake. And that gives you a chance to forecast how that sequence is going to behave in the future. So aftershocks represent an increased earthquake hazard that can remain elevated for months, years, or decades. And that's what we're trying to describe with the forecasting. Okay, why forecast aftershocks? If you can't forecast the main shock, we typically think of aftershocks as being smaller than the main shock. So what's the point of forecasting the aftershock if you can't forecast the main shock? Well, aftershocks themselves can be damaging, and aftershock forecasts provide situational awareness. They give emergency managers a sense of what they can expect and what the hazard that the community is exposed to. Aftershock forecasts also increase public resilience. So people are living in the region affected by earthquakes. They're feeling earthquakes every day. If you can put out a forecast that says what you're feeling is normal and give people a sense of what to expect in the future, that really increases the psychological resilience of that population. When those large aftershocks do happen, they know that it was something normal and expected, so they can kind of accommodate that occurrence easier. And of course, ideally, it would help decision makers to prioritize the response and recovery if they had some quantitative information about how likely they were to be affected by a large aftershock. And so a really good example of a case where the aftershock, even though it was smaller than the main shock, was actually much more damaging than the main shock is the Christchurch earthquake sequence in New Zealand. So this was a sequence of earthquakes that happened in 2011. The main shock was out in a very unpopulated area. It was a magnitude 7.1. All of its aftershocks here are shown in green. It was a significant earthquake, but it didn't do too much damage. But it had a magnitude 6.2 aftershock that happened to occur right in the middle of the center of this town of Christchurch. And it devastated the city just because it occurred right underneath all of the heavy construction. So even though it was smaller than the main shock, it was far more damaging. And then the sequence went on to have additional large aftershocks that caused additional damage. So by forecasting aftershocks, you might not get the biggest one, but you can still get the ones that cause the most damage. Another example of a large aftershock that had serious impacts was in the 2015 Gorkha, Nepal earthquake sequence. So on April 25th, 2015, there was a magnitude 7.8 earthquake shown by the star here, which caused thousands of fatalities, tens of thousands of injuries, almost 750,000 homes damaged, people affected. But then the magnitude 7.3 aftershock, so a few weeks after that, there was another earthquake, smaller, 7.3, but it still caused 200 fatalities, greater than 2,500 injuries. So even if we can't predict this one, we can, or forecast this one, we can still kind of help people plan for these large aftershocks that can still have a pretty major effect on the population. Furthermore, we tend to think of aftershocks being smaller than the main shock, but that's not always the case. Aftershocks can in fact be larger than the main shock. Once that aftershock happens, that's larger than what we were calling the main shock previously, we redefine that previous main shock as a foreshock, and then we call the largest earthquake the main shock. But you can really think of these as aftershocks that are larger than the main shock. So an example of this would be in 2016 in Japan, the Kumamoto earthquake. There was a magnitude 6.2 earthquake, main shock, but then one of its aftershocks turned out to be even larger and ruptured up to the northeast, a magnitude 7 aftershock, which was then called the main shock. So when we talk about forecasting aftershocks, we're not just talking about earthquakes that are smaller than earthquakes that happened before. We're also including these earthquakes that are larger than their main shock. So we're including these foreshock sequences. So that has a lot of value. So who uses aftershock forecasts? Here's a news article in California where this is kind of we put out a warning after there was a magnitude 6.4 here that there could be larger earthquakes. Usually there isn't a larger earthquake. In this case, there was. But who uses aftershock forecasts? I think our primary audience is the public and the media, because we have a lot of people who are really upset, who are experiencing a lot of earthquakes. It's kind of a traumatizing experience. So we need to communicate to the public that we know what's happening and we know what they should expect. And that really helps the public be resilient against the disaster. We've seen this in a number of countries, where if people understand that what's happening is normal, then they can respond much more effectively to it. The other audience for forecasts would be emergency responders, who can use this quantitative information to understand, their risk, how much risk they're exposed to. Search and rescue, these are people going into buildings in the first few days after an earthquake, and they really need to know how exposed they are to large damaging aftershocks. And then lifeline operators, things like utilities, roads, and electricity, they can use this information. And then over longer timescales, the people who are going to be doing the reconstruction, insurance companies can use this information to figure out how much reinsurance to buy. Embassies, we often find at the United States Geological Survey that we're giving forecasts to US embassies abroad to help them in the emergency response. And then scientists. So as geoscientists, when we issue a public aftershock forecast, that's the ideal prospective test of our models, because we've gone out and we've put a forecast out in the public. We can't change it. We can't change our model. All we can do is wait and see how that forecast plays out. So it's really the ideal test of the scientific models that we're using to describe these sequences in the first place. So forecasts are useful over both the short term and the long term. Aftershocks concentrate in time close to the main shock. They're heaviest early on in the sequence, and then they slow down over time. But if you consider that, so they decay very rapidly early on, but one of the features of aftershocks is that once they finish that early decay, they decay much more slowly. So even though they decay quickly, they have a large tail at long time. And this is demonstrated very nicely by looking at the aftershocks of the Northridge earthquake in California. So this was an earthquake in 1994, magnitude 6.7. You can see some of the damage here where it knocked down some of the freeways. But if you look at these plots here, it's showing the magnitude of the aftershocks versus time since the main shock right here. You see that decay in the aftershock activity over this first week. So this is days. But then if you zoom out to 1 year, you see again, basically the same pattern. So all of the activity is concentrated at the beginning, and it shows this long-term decay. It's almost like a fractal process, where if you zoom out again a decade, you again see the same pattern, where even though the aftershock activity is concentrated early on, you really see the effect of the elevated seismicity rate out to years and decades. I'm not sure that this has gone back to the background hazard in this area. I think around this Northridge earthquake actually remains one of the most likely places to see additional earthquakes in the future in California. So what's the relevance of this? What does it mean that aftershock hazard remains elevated many years after the main shock? Well, it helps to think about the time scale over which you're exposed to aftershock risk during different stages of the response and recovery and restoration after an earthquake. So this is kind of a long-term aftershock forecast for a hypothetical magnitude 7 main shock. These are numbers generated from like an average model for an earthquake forecast, just to look at the probabilities of being affected by a large aftershock during different stages of the response and recovery. So of course the aftershocks are most frequent in the early times. So if you think about emergency response, putting out fires, search and rescue inside of buildings, establishing shelters, inspecting buildings to see which ones can be reoccupied, all of this is happening in the first couple of weeks. And this is the most active time. and the highest risk time. Over those 2 weeks, there might be a 60% chance of seeing an aftershock as large as magnitude 6, which could cause additional damage and really affect those emergency response efforts you're doing. When you think about longer time periods, after those first 2 weeks, you're talking about restoring utilities, water and gas. You're talking about removing debris. You're talking about putting in temporary repairs. You might be doing that for the first 2 weeks to a year. But over that time period, because it's even though the aftershock rate is lower, you might not be feeling aftershocks every day. Because the time period is longer, your exposure is actually still quite significant. And this is true even going out to response operations that go out to years or decades. So in reconstruction, when you're talking about rebuilding structures and you're going to have a work crew on scaffolding or inside of partially constructed buildings, that's a really vulnerable place to be. And if you're going to have people there every day for 3 years, then even though the aftershock rate has dropped down quite a bit per day, over those 2 years, the exposure again might be pretty substantial. So, and this continues as you go to longer and longer term response projects. That exposure to an aftershock sometime during that period in which you're responding is substantial. So aftershock forecasts are important in the first days, but they're also important, 10 years after. The hazard remains elevated for years or decades after a big earthquake. So let's talk a little bit about the physics of earthquakes or of aftershocks, what causes aftershocks. We have, a fairly good understanding of why aftershocks follow a big earthquake. The first way that you trigger aftershocks is by static stress transfer. So of course, the big earthquake happens when the stress builds up and exceeds the strength of the fault slips. That stress is relieved on the first fault, but it gets redistributed to all of the other faults. And so this is a map showing an earthquake in California in 1992, the Joshua Tree earthquake, showing a calculation of the stress changes due to the earthquake on this fault. That little star is the epicenter. And the purple lobes are showing regions in which the stress was relaxed, it was decreased. The red lobes are showing regions in which the stress was increased. And if you look at all these white dots, those are the locations of the aftershocks of this earthquake. And they really seem to fall primarily in these regions where we think that the stress increased. So this is one of the main ways that you cause aftershocks. You just push that stress down the line to other faults within the system. The other way that you trigger aftershocks, so the static stresses are very important in the very near field, close to the previous main shock. But there's also a way that you can trigger aftershocks more distantly, and that's the seismic waves themselves. We call this dynamic triggering. And so a good example of that is the 1992 Landers earthquake in California. Basically the same location as that previous earthquake we were looking at. That earthquake happened right here. And then that turned out to be a foreshock of a larger earthquake, this Landers earthquake, which was magnitude 7.1. And so this region in here is showing all those black dots are aftershocks that are related to that static stress mechanism. But this was a really surprising earthquake in that it increased seismicity rates all the way thousands of kilometers away from the main shock over basically the entire western US. And this earthquake started down here and ruptured to the north. And so it generated a lot of directivity in that seismic wave up to the northwest. So all of these regions, or all of the faults in this region, were exposed to really high shaking and popped off in aftershocks even 2,000 kilometers away. So we know that aftershocks are related to stress, whether it's static or whether it's dynamic stress resulting from the passage of the seismic waves. But the bad news is, even though we understand what causes the aftershocks, we still can't make physics-based forecasts because we don't have information about the pre-existing stress state. This goes back to that slide I had in the beginning showing that, when you have the earthquake really depends on how close you are to that failure threshold. And we just don't know how close you are to that threshold anywhere in the crust. It's very hard to measure the absolute stress and then how close faults are to that limit. The good news is that even though we can't make those physics-based measurements, we can still forecast earthquakes using statistics of past aftershock sequences without knowing the exact stress state. So this is illustrated by this pile of equations here, which give you kind of a statistical representation of what to expect, even when you can't model the physics. I want to take a moment to talk again about foreshocks, main shocks, and aftershocks. So I think you know, the lay understanding of foreshock, main shock, and aftershock kind of considers these different types of earthquakes. You know, main shock is big, aftershocks are small, foreshocks are small. Like there might be some different physics. In general, foreshock refers to a smaller earthquake that precedes a larger earthquake. Aftershock refers to a smaller earthquake that occurs after a larger earthquake, just before and after. And then the main shock is the largest earthquake in the sequence. But when you're actually assigning these titles in an active sequence, all of these names can be changed. So the main shock title can be passed along if there's a larger aftershock. So a lot of sequences will generate, or about 5% of sequences generate an aftershock that's larger than the main shock, in which case you rename the main shock a foreshock, you rename the aftershock the main shock. But physically, these are all earthquakes, and they can grow to any size once they get started. It's the main shock. A large earthquake sets off a bunch of earthquakes. They can have any size. Usually they're smaller, sometimes they're bigger. So I wanna discourage you from thinking about these as different earthquakes in a physical sense. It's really just they get started and then they grow as large as they want to be. They're all earthquakes and they all obey the same physics. And that means that an aftershock rarely can grow even larger than the earthquake that set it off. And this is easy to see in the data. So if you look at this figure here is showing the survivor function. So the complementary cumulative distribution function. It's showing the fraction of earthquakes that are larger than a given differential magnitude relative to the main shock. So the main shock here is shown at differential magnitude 0, and then the blue curve is showing the distribution of sizes of the aftershocks. So all of the aftershock, or all of the curve to the left of this line is showing aftershocks smaller than the main shock, and then the curve to the right of the line is showing aftershocks that are larger than the main shock. And it's a very small percent of aftershocks that are larger than the main shock, but you can see that the statistics do not notice the magnitude of the main shock. The statistics don't know about foreshocks, aftershocks, and main shocks. All the statistics tell you is that if you trigger an earthquake, it's going to have a magnitude that's drawn randomly from the distribution of possible magnitudes. It could be smaller, it could be bigger. And a few percent of aftershock sequences include an aftershock larger than the main shock. So this is just again to emphasize that these aftershock forecasts include the large earthquakes that we might be most interested in that are following smaller earthquakes. So rather than thinking about foreshocks, main shocks, aftershocks, the modern way of thinking about this is as an earthquake epidemic. So we think of earthquakes and aftershocks in general as a self-exciting process. When there are a lot of earthquakes, those earthquakes trigger more earthquakes, so self-exciting. And this is exactly how an epidemic works. So in this case, large aftershocks are like new outbreaks in the epidemic. And there's no need to really identify a main shock or foreshock or aftershock. We just recognize that each earthquake temporarily raises the probability of further earthquakes. And each earthquake has some small chance of being a foreshock. So you have the main shock, which triggers primary aftershocks. Those primary aftershocks themselves have aftershocks. If you have a large one, then that's like an outbreak in the epidemic, and that can trigger, you know, multiple generations of aftershocks, kind of ad infinitum. So a good example of a sequence that was like this is that Christchurch sequence in New Zealand, where you had the main shock and then the large aftershocks. And if you look at that data, the total number of aftershocks as a function of time, you see that it's this sequence of outbreaks where you have a rapid rate of accumulation of aftershocks. It starts to decay, but then you have a big aftershock, which, you know, reinvigorates the epidemic. And so this is the model that we use currently to forecast aftershocks. So before I get to the detailed, the details of the equations that we use to do the forecasting, I just want to go over kind of the rules of thumb, the basic rules that we use to forecast earthquakes. A lot of our detailed forecast models are really just kind of modifications of these, or modifications of these basic rules that we know about earthquakes. So there are kind of 3 rules that you have to know in order to forecast earthquakes. The first is the productivity law. And this just states that larger earthquakes trigger more aftershocks. And in fact, it's a factor of 10 more aftershocks for each unit of main shock magnitude. So if you're thinking of a main shock of magnitude 5 and the number of magnitude 3 aftershocks it would trigger, so that's the number of felt aftershocks it would trigger. 3 is about where you start to feel them. Well, a magnitude 5 is going to trigger about 7 magnitude 3s on average in the first week. Magnitude 6 is going to trigger 10 times as many. Magnitude 7, 10 times as many again. Magnitude 8 again. So these circles are scaled to the area. The area is scaled to the number of aftershocks you'd expect from each one of these main shocks. So this is really the primary statistical rule that we're using in the aftershock forecast, is this productivity as a function of main shock magnitude. The second rule we use is the Gutenberg-Richter law. This is just the earthquake size distribution, which applies to all earthquakes, including aftershocks. And it states that most earthquakes are small, and that there's a factor of 10 fewer aftershocks for each unit of increase in magnitude. So if we're thinking about this magnitude 8 that triggered all of these aftershocks, 7,000 aftershocks. Well, what's the size distribution of those aftershocks? There might be 7,000 magnitude 3s, but when we think about magnitude 4s, that gets divided by a factor of 10. So we might expect 700 magnitude 4s, 70 magnitude 5s, 7 magnitude 6s. So this describes the size range of the aftershocks that we expect. And then the third rule describes the distribution in time. We talked earlier about how the aftershocks are concentrated at the early times after the main shock, and then continue out to long time. So the statistical rule that we use is that the aftershock rate is proportional to 1 time since the main shock. And this is shown really nicely for an earthquake in Japan. So Omori was a Japanese professor, and he was studying this earthquake, the Nobi earthquake, which occurred in 1891 in Japan. And he was measuring the number of felt earthquakes and found, so there's a log-log plot where you've got factors of 10 in time on the bottom and factors of 10 in the rate of daily earthquakes on the vertical. And you can see that it just decreases continuously as 1 over the time since the main shock. Even out to, here's 1970, this aftershock sequence has been going on for more than 100 years and just continually following this 1 over time decrease in activity. So again, this means that even though the aftershock rate decays very quickly at first, it takes progressively longer and longer to get to equivalent aftershock rate decreases. So we call this a very heavy tail distribution. Decays rapidly, but then it has a very heavy tail, persists for a long time. But since aftershock rate does decay so fast at early times, it really matters whether you can get a forecast out quickly or not. So timeliness of the forecast really matters. So one of the rules of thumb is that if you consider all of the aftershocks that happen in the first year, 50% of those aftershocks actually happen on the first day. So the first day has half of the aftershocks that you'll see over the entire year. And of course, aftershocks persist longer than a year. They can persist decades, but of those earthquakes that happen within the first year, half of them happen in the first day. So it's really important to have these foreshock or these aftershock models ready to go as soon as a main shock happens, because that's really the moment when you can kind of make the best use of the information. So to recap the kind of rules of thumb, the basic scalings that go into the aftershock forecasting, statistical aftershock forecasting, you expect about 1 aftershock within 1 magnitude unit of the main shock. So that's kind of the most important scaling law. If you had a magnitude 6 main shock, you can expect at least 1 magnitude 5 aftershock, or 50% of the time you're going to see an aftershock as large or larger than magnitude 5. If you had a magnitude 7 main shock, then you'd expect at least one aftershock of magnitude 6, 50% of the time. And that goes to the second rule, which is that you expect 10 times more aftershocks with each additional unit of magnitude. So a magnitude 6 main shock makes one magnitude 5 aftershock, that we just said, but it also makes around 10 magnitude 4s, 100 magnitude 3s. That's that factor of 10. And then a magnitude 7 would make 10 5s, 100 4s, 1,000 3s. And then the time rule you can think about in terms of there are going to be 100 times fewer aftershocks on the 100th day of the sequence as on the first day. There are going to be 10 times fewer aftershocks on the 10th day than on the first day. So that's the temporal decay. That 1/time relationship means that, you know, the first day, the second day, you're going to see half of what you saw on the first day. The third, you'll see a third. And that's pretty well borne out by these sequences, except unless you have a large aftershock that, you know, increases the rate again. And then finally, about 1 out of 20 sequences turns out to be a foreshock. So kind of the take-home message there, I love telling people this: if you felt shaking in the earthquake, there's a 5% chance, 1 in 20, that you'll feel similar or worse shaking again. So this is, you know, this is kind of the basics of the forecast. If you were like talking to reporters about what to expect in a sequence, this is kind of all you would need to know, these basic scaling laws. But of course, we can get more specific with the more elaborate statistical models. So there's a fourth rule about the spatial distribution of aftershocks. So aftershocks, earthquakes in general tend to occur where earthquakes are happening. Your best guess of where the next earthquake is going to happen is where, you know, the earthquake rate is high. And that's true for aftershocks as well. They cluster around their parent earthquake. The future earthquakes tend to be, the future aftershocks tend to be located very close to the previous aftershocks. And so that gets modeled as a spatial probability kernel or a spatial probability model. And so this is showing the fraction of earthquakes remaining as a function of distance from the aftershock centroid, the center of that aftershock zone, which is close to usually close to where the main shock happened. But what we know about the spatial distribution of aftershocks is that the size of the aftershock zone increases with the magnitude of the main shock. So these different curves, the solid lines here are observations and the dashed lines here are a model fit, but the colors go with the main shock magnitude. So you can see this zone increasing in size as a function of the main shock magnitude. And then outside the rupture length, basically outside the main rupture, the aftershocks decay quite rapidly. So yeah, the takeaway is large aftershocks have large main shocks have large aftershock zones, and most aftershocks occur very close to their own main shock. So this feature right here, most aftershocks occur very close to their own main shock, is really interesting when you start to consider this epidemic type model for aftershock occurrences. So in the epidemic type model, you don't have a main shock and aftershock, you have these multiple generations of aftershocks. The main shock has aftershocks, the aftershocks also have aftershocks, and those aftershocks have aftershocks, and so on. So what this means is that the occurrence of those early aftershocks gives you a really good idea of where the subsequent aftershocks are going to happen, because they're going to happen close to their parent earthquake. So secondary triggering is concentrated near the previous aftershocks. And so as an example, I've got here the earthquake in Nepal in 2015 showing, so here this ellipse here is an estimate of the main shock rupture, and then all of these little circles are the early aftershocks. So this is a plot showing all of the aftershock activity in the first day after that magnitude 7.8 main shock, which started up here. And then the contours are showing basically this model, showing the aftershock rate expected from that kind of spatial distribution kernel. And what you see is that mostly there's a bullseye around that ellipse, but then you also see all of these hotspots associated with the smaller earthquakes. And as you go forward in time, the spatial distribution responds to the occurrence of new aftershocks. So especially in this region in the southeast, you see there's a high number of aftershocks. As you go on to a couple weeks after the main shock, you see you've had a large aftershock out here, and the activity remains elevated down here. This is a real hotspot in aftershock activity. You see these contours bulging out in that direction for that reason. And sure enough, 3 weeks after the main shock, you had that magnitude 7.3 aftershock. So that's shown by this big circle here, which again triggered a bunch of its own aftershock activity. So in terms of the epidemic model, you could think of this large aftershock as a super spreader, which caused a bunch of its own secondary aftershocks. And so right after this large aftershock, even though it was 0.5, it was half a magnitude unit smaller than the main shock, because it triggered so many earthquakes, this is actually the region of the highest hazard down here in the southeast, close to this aftershock. And that remains true even a year out after the occurrence of that main shock, where this region of high aftershock activity remains the region of the highest hazard. This is the most likely place, just from the statistics, this is the most likely place to see another large earthquake within this sequence. So, okay, so this is the spatial forecast. So we've gone from just predicting kind of the magnitudes, the numbers in general, to predicting where they might occur. The last step that is really useful in doing these aftershock forecasts, you know, it's helpful to know that there's going to be, you know, a certain probability of magnitude 5 somewhere, but it's a lot more useful to understand, you know, what is my chance of being affected by shaking in my particular area. And so to do that, we can bring in ground motion prediction equations. So we can actually, from this rate model, we can predict expected ground motions. So to do that step, we use ground motion prediction equations. These are, again, empirical models where people have gone out and measured the shaking at specific instruments for a range of magnitudes and a range of distances. And this gives you an empirical model for how much you should expect to shake with uncertainty as a function of the magnitude of the earthquake and your distance from it. And you know, usually we apply these to earthquakes that we already saw. We do for the USGS shake map, which you may be familiar with, where we've just had an earthquake and we want to estimate how badly the area has been affected. We use these ground motion prediction equations. And we also use things like the shallow seismic velocity to figure out how much that shaking is going to be amplified at different sites. So here's a map of the LA basin, Los Angeles, showing high amplification in the basin, lower amplification in the mountains. And this is something that's true around the world. So we can take these ground motion prediction equations and then these site amplification effects to get an estimate of the amount of shaking that you're going to get from those earthquakes that you're forecasting. So to summarize that, we start out with the aftershock locations, times, and magnitudes. This is an example based on the sequence of earthquakes that's ongoing right now in Puerto Rico. Started in 2019, it's continued through 2020, and this is the location of all the aftershocks that have occurred so far. So we take those locations times magnitudes, we plug them into the statistical models, describing the productivity as a function of magnitude, describing the size distribution of the aftershocks, describing the temporal distribution of the aftershocks, and the spatial distribution to get a map of the aftershock rate. So this is the instantaneous estimate of the aftershock rate, and then we plug that into a shaking model using those empirical ground motion prediction equations and the site amplification to go to a shaking forecast. So this last slide is showing the probability of exceeding intensity 6, intensity 6 being the level of shaking where you should expect damage within the next month. And you can see that right now in Puerto Rico, there's a 10 to 20% chance of seeing damaging shaking in the next month in some of these populated areas. Okay, so to take this, those were the rules of thumb. If you want to take this to the kind of advanced level, this is the actual equation that we use in the epidemic type model. So this equation is showing the total expected aftershock rate as a function of time since the main shock and above some magnitude n. And this is showing how it's this summation sign is showing us the combined contributions from all past earthquakes in the sequence. This is what makes it an epidemic-type model. It doesn't matter what size you are, you have a contribution to the aftershock sequence. It's bigger for larger magnitudes, and that's described in this productivity law, where you have this 10 to the magnitude of the earthquake. So that gives you that factor of 10 per unit of magnitude. And then you have the temporal decay described here. This is that Omori's law, or temporal decay component of the model, where you have the time since the previous earthquake to some decay constant. And you just sum up all the contributions from past earthquakes. And then this is the core model, and then differences between sequences are all captured in differences in the parameters. So when we talk about building forecast models, we're really talking about estimating those parameters. So that involves fitting a forecast model to the aftershock sequence. Now we're into the real nitty-gritty, and we're talking about, you've got an aftershock sequence. How are you going to actually fit this model to the aftershock sequence, and how are you going to go forward with that model? So at time 0, let's say you just had the main shock. Well, the only information you have so far is the magnitude of the earthquake. So if you want to issue a forecast, you don't know anything about the current sequence, so your only option is to go look at past sequences. So what we do is we start out by fitting an average model to all past sequences in the region. So that's this model, but we're estimating those parameters for every earthquake that's occurred in a similar tectonic environment going back 20 or 30 years. And we're not just fitting the average, but we're finding the average and the variability between sequences. We want to know the full range of what could happen in this sequence. And we call this model a generic model. So this is the starting forecast model. And then as time goes on, and we actually have aftershocks play out in that sequence, we get some more information about whether that sequence is particularly active or quieter than average, and then we can update that model. So, but the generic model, that starting model that's based on average past behavior, is still used to regularize the forecast. If you have some familiarity with statistics, we use a Bayesian updating procedure where we start with the estimate that is based on the past, and then we don't really allow the new estimate to differ from the past unless we have very clear evidence. So the Bayesian updating is a way to update that forecast model only to the extent that the data really justify. And this is crucial to getting stable forecasts that kind of vary smoothly during the update process. Otherwise, it would be very easy to overfit a sequence and kind of get the parameters wrong. So it's very helpful to condition the current fit on what you've seen in past sequences. And so here's an example of what those generic models might look like for different tectonic environments. This is a map showing the typical magnitude of the largest aftershock in a sequence relative to the main shock for various tectonic environments. I said earlier that that number is about, the largest aftershock you can expect is about 1 unit of magnitude smaller than the main shock. In fact, it's about 1.2 units smaller than the main shock. And the map is showing, so here the yellow colors are high productivity sequences. Generally in subduction zones and convergent margins, you have very high productivity. And then in more stable continental environments, you get kind of medium productivity. And then in the ocean, where the crust is thin and hot, you get much lower productivity. So this is just showing the spatial variations in those starting generic models. If you have an earthquake in a subduction zone, you're going to assume it's going to have more aftershocks than if you have an earthquake on the East Pacific rise or something. And then those, so this is just showing a point estimate, but of course the parameters in those models are actually distributions. When we fit the model, we fit it with a distribution. And that's to capture the uncertainty in the model. If you just took a point estimate, you wouldn't capture the uncertainty you had in the model, and it'd be easy to overfit the sequence. But by using kind of a full distribution of what those parameters could be, then you correctly propagate your uncertainty in the model into your forecast. And that prevents you from being surprised. Even though it might widen your confidence interval, it's going to prevent you from being surprised later on in that sequence. So we start out with the generic model based on past activity. But then once the sequence starts playing out, we start to get information about that specific sequence. So this slide is showing kind of an illustration of that sequence-specific model updating. This is for an earthquake that happened in Mexico, just south of the California border, showing the cumulative number of aftershocks versus time since the main shock. The black curve is the observed aftershocks, and then the dashed line there is that epidemic-type aftershock sequence fit. And then these frames are showing you those parameter estimates. And so you can see right up here, this parameter is the productivity of the main shock. And the thin line here is the average, the range of behavior seen for past sequences, the same in each of these panels. And the blue here is the estimate that we're getting based on a Bayesian updating based on the current sequence. And so you can already see that this sequence is on the higher end of productivity, but some of the other parameters are either unconstrained or close to those long-term averages. But then as time progresses, this is after 1 day, after 7 days, those distributions start to narrow. We start to get more confident about what the parameters of this particular sequence are. And that lets us give a more specific forecast with narrower confidence bounds as time goes on. And so if we wanted to look at how this would play out during a sequence, actually a sequence which turned out to be a four shock sequence, we can look at another earthquake in California. This was the 2019 Ridgecrest earthquake sequence. It started with a magnitude 6.4. It went on to have a magnitude 7.1. But if we look at the forecast, so this is a forecast we issued at basically 0 days. The only information we had was that magnitude of the first earthquake. So we have a probability distribution for all of the parameters. Here I'm showing, its productivity, how many aftershocks it's going to have as a function of its magnitude. And this distribution of parameters corresponds to a distribution in the forecast. So this panel is showing the number of aftershocks we expect exceeding magnitudes on this horizontal axis. The solid line here is the expected number. So we're expecting, around 90 magnitude 3s in the first month, maybe 1 magnitude 5. And that corresponds to this estimate of the productivity in the middle. Then the lower bound and the upper bound correspond to those tails of the distribution, respectively. And then as time goes on, so this is the generic forecast based on past activity because we're at time 0. But then even after just 0.1 days, we see that this sequence is much more productive than average. So our estimate of the productivity goes up, the forecast goes up a little bit, and the range narrows down a little bit. And then as time progresses, we continue to get more confidence that this is a highly productive sequence. This distribution narrows, and this forecast goes up. It also goes down just with passage of time since the main shock. And then finally, after 1.4 days, we have the occurrence of that main shock. And you can see there's a big adjustment to the parameters at that time. So the main shock here, the foreshock was very productive, more productive than average. But the main shock itself is actually closer to average. So now the estimate we get for the productivity parameter in this model actually drops when the main shock happens, but the forecast goes up because you just have this large shock, which is going to trigger, or this large, I guess, shock now you would call it. It's an aftershock of the earlier one, but since it's bigger, now we're going to call it the main shock. It now has raised the hazard quite considerably from the day previous. So that's kind of how the epidemic model plays out. You just keep watching the sequence. Whenever there's a big earthquake, that raises the probability that you're going to have continued more earthquakes. So to actually generate a forecast with this model, this is the model we fit. We got the parameters, we have the equations, but then to actually generate what we expect to happen in the future, we need to generate simulations. So the basic recipe for generating a forecast is we have this distribution of parameters that we think correspond to the sequence. So we sample a set of parameters, a single set of parameters from the distribution of possible parameters, a unique set of parameters for each simulation, and that captures the epistemic uncertainty, the uncertainty we have in the model. And then for each past earthquake, parent earthquake in the catalog, we calculate based on the model how many aftershocks we expect it to have within our forecast window. And then we generate a random number of aftershocks based on that value, based on that expectation for each one of the aftershocks that have occurred so far. Then we assign times and magnitudes based on those scaling laws that we talked about earlier. And then so this gives us a new generation of aftershocks. The next step then is to go back to step 1. And for all of the aftershocks that we simulated, we have to ask, well, how many aftershocks are they going to contribute? So we need to consider, do the whole thing again for the aftershocks to get a second generation and a third and a fourth. And we continue this until the epidemic finally dies out. We get a generation that includes no new aftershocks. So then we just, 10,000, 30,000 times generate a bunch of catalogs so we really see the range of what could happen in this sequence. So this is showing that cumulative number versus time, showing various possibilities for how the sequence could play out. Some of them don't have any large aftershocks and they stay low. Some of them do have large aftershocks and they get kicked up high. But we can define things like the median and the 95% range within this set of simulations. And then we can tabulate that into a forecast. So the forecast is based on what comes out of the simulations. So this is kind of the basic forecast product. It's probabilities and expected numbers of earthquakes as a function of magnitude of the earthquake and the interval over which we're forecasting. So if we think about, say, that's this 1 month interval, we might expect hundreds, 500 felt earthquakes of magnitude 3, but maybe only 1 earthquake of magnitude 6. And the associated ranges are over here. And then we also have the probability that we'll see at least 1. So there might be a 41% chance of seeing a magnitude 6 in the next month, a 5% chance of seeing a magnitude 7. These probabilities are just a fraction of the simulations that included an earthquake fitting that description. So the table is a little bit hard to parse. It can be, especially in a stressful situation like an active aftershock sequence. So we've currently at the USGS been experimenting with some visual ways to communicate these probabilities. So you might see a table like this where it's showing just these probabilities that are in this column here as a function of magnitudes and duration, but kind of shown as a bar graph with colors that give you an idea of what the impact of those earthquakes would be. And then, of course, we go making maps to give you a sense of, if I'm living here in this town of Ponce, then this is telling me what my likelihood of being affected by the earthquakes in this region are. Okay, so the forecast models are pretty well established. Right now, in terms of the state of the art of the field and future directions, what people are working on right now in the field of aftershock forecasting is assessing the model performance and really trying to establish a prospective testing method where we can, we're putting out these forecasts. It's crucially important that we make sure that the forecasts are working. So current efforts are focused on developing prospective testing and validation of the models. This is an example of testing of the model for that Puerto Rico sequence. We've been putting out these epidemic-type forecasts since January of this year, and now we have this record of prospective tests of the model. And so this matrix here, these figures are showing the residual. The colored lines are the forecast range, and then the flat line here is how many we actually observed. So these are showing the residuals between the forecast and the observed number for a day, a week, a month, magnitude 3s, 4s, and 5s. And you see that the model does pretty well. It's capturing, what you want to see is that this solid horizontal line is between the ranges of this forecast. And it's not perfect, but it does a pretty good job. And we'll be continuing to evaluate the forecast as we go forward. So to summarize, we are unlikely to get predictions anytime soon, be able to say when and where an earthquake is going to occur with certainty. But in the meantime, we do have forecasts. And so just like long-term forecasts based on geology tell you what to prepare for over years and decades, a short-term forecast based on statistics tells you what to expect over the next weeks and months and helps you plan for those low probability but high impact events, meaning that 5% of sequences that turn out to be foreshocks. So, I don't know what actions you should specifically take in response to one of these aftershock forecasts, I usually tell people that, that if you get a table of these probabilities and you don't know what to do with it, then just treat it as a reminder that you live in an area that's affected by earthquakes. And so whatever steps you do to prepare for earthquakes, if you receive a forecast, don't worry too much about the numbers. Just take those steps that you do to prepare for earthquakes, whether that's store additional food, work out your emergency plan with your loved ones, whatever it is that you do to prepare for that eventuality. Your aftershock forecast is your notice to do that today. So that's really all I want to go into in terms of the methodology. With the last kind of few minutes, I want to run through an example of generating a forecast with the software that we have developed at the USGS. So this is an image of the graphical user interface for this software. And it's fairly flexible. There are a lot of options, but the workflow is fairly simple if you don't need to customize it too much. And what it does is you basically give it a USGS, you give it an earthquake event ID, and it'll go to the USGS servers to pull data down. It'll bring that into the program. It'll estimate that epidemic type aftershock sequence model. It'll estimate the parameters, get those distributions, then generate a bunch of those stochastic event sets, and then spit out a graphical summary of that forecast. So here's that graphical user interface. So the first thing you need to do is give it a USGS event ID. This is actually one of the more challenging aspects of using the software, is actually finding this event ID because it's specific to the USGS catalog. So where you would find that, you would have to find that by going to the earthquake.usgs.gov website and looking at their earthquakes page. And you could either find the earthquake you were looking for in their earthquake map, or you can find it in the catalog search tool. But ultimately, once you find your earthquake, and it has all of this information about your earthquake, including an aftershock forecast in this case, because it's Puerto Rico, which the USGS did issue a forecast for. But the USGS event ID is up here in the URL. It's in some other places, but the easiest place to find it is in the URL here. So we take that and we plug it into the software, then we'll start, we have our options here. We can generate the forecast beginning at the current time, or we could do something earlier. We could do it at 0 days after the main shock, 1 day after the main shock, or we could generate this forecast for sometime in the future. But let's just go ahead and start it at the current time. And then once we've decided that, we just click fetch data. And so this will query the USGS servers. It may take a moment. There we go. So it found a number of aftershocks. It's keeping only the 1,000 largest, just to keep the computation fairly quick. And it's going to show us some summary of the sequence so far. So here's a map of the earthquakes that have happened so far in that sequence. The colors correspond to the time of occurrence. So you see all these dark ones, those were early on in the sequence. And then this is a pretty interesting one. The lighter colors are all to the west and the east. And this sequence of earthquakes has kind of spread out to the east and west over time. We've had a lot of magnitude 5 aftershocks that have extended this aftershock zone out to the east and west. It also shows you a magnitude versus time plot. So here's that magnitude 6.4 main shock, all of its aftershocks, including some large magnitude 5s that trigger their own little outbreaks in the epidemic. We can look at the magnitude number distribution. This is the relative number of small versus large earthquakes over that sequence. And then the cumulative number plot, where you're looking at the total accumulated number of aftershocks versus time. So this is just to show you what's happened in the sequence so far. The software has some options. If we didn't like this aftershock zone, this dashed line, we could edit it, make it bigger or smaller. We could load in a local catalog from our own regional network. But the next steps here are to estimate the model. So the the software starts out by, based on the location of the main shock, it assigns it a tectonic regime. So here it's decided it's a generic subduction zone earthquake. So it's going to start with those initial parameters for the forecast. And we could go in and edit the range of possible parameters, but we'll just click compute model fit. So now what it's doing is just estimating those parameters for all of these earthquakes that have occurred so far. So we'll give it a second to think. Okay, so the black line again here is the observed number of aftershocks versus time. This dashed line is the model estimate. So you see it's not perfect, but it's pretty close. This sequence was a bit more productive early on in the sequence than is really captured by the model, but it does a pretty good job. And the next thing we can look at is those distributions of parameters. So if you remember those plots I showed you earlier where we had the generic model, this is the range of values that we've seen in past sequences. And then the blue is the range of values that we estimate for this sequence. And so you see, again, this is another sequence where the productivity is very high compared to the average. So this first parameter is just the productivity of the main shock, the primary productivity. The next parameter is the productivity of the aftershocks, the secondary productivity. And again, that is very high relative to the average, extremely high, really right at the top of anything we've seen in the past. This Puerto Rico sequence is the most active sequence I've seen in my entire career of looking at aftershock sequences. And that's shown in these parameter estimates, which have the productivities really high. However, the other parameters, like the temporal decay that we talked about, so the p-value in Moore's law, if you're familiar with that, this is the parameter that describes how quickly the activity falls off with time. And that's actually very close to the average, where as the sequence has gone on, we've just gained more confidence that it's close to that average defined by that thin line generic model. And there's some other parameters that we can look at just to make sure that the estimate makes sense. So once we have those parameters, then we go to the next step, which is to generate a forecast. So I'm clicking here, run specific forecast. And so what it's doing right now is it's following that recipe that I described, where 10 or 30,000 times it's generating a hypothetical aftershock forecast or a hypothetical aftershock sequence based on the parameters and the earthquakes that have occurred so far. So each one of the past earthquakes is a seed for future earthquakes generated randomly. And this will take a few seconds to calculate. But so in each step, it's randomly drawing a value from these distributions. Most of the picks will be close to the mode of the distribution, but it will also sample from around here and here. So this is really important for doing the forecast, that it really capture your uncertainty that you have in those parameters. Otherwise, you'll get an over-specific forecast, which you'll have high confidence in the forecast, but it'll be wrong frequently. So it's really important to look at the full range of possible parameters that describe that preceding seismicity. This should only take a few more seconds. I want to leave enough time for questions. I think I only have 15 minutes, so I'm actually going to jump ahead to, once this gets done, we'll see some plots showing the expected possible outcomes of this sequence. Then we'll be able to plot a map of the aftershock rate spatially, and then we'll be able to publish that forecast to an advisory document. I'm just going to go ahead and open that document right now. So this is one I prepared earlier. And this is showing the results of those calculations. So ultimately, the software outputs this document, which is an HTML document. It's interactive, so you can look at the different products. So here's that rate model. Here's that number versus time. The purple here is showing an average sequence, that generic model that was described by that thin line. And the green is showing this actual specific sequence, which is much more productive than the average. You've got the table of probabilities. You can look at different products like the magnitude distribution for different time intervals, and or just go back down to that fundamental table of probabilities. Yeah, so it finished there, but, and then we can go on to generate the map and publish it. But here's the result of that. So that's what the software does. I haven't, there's a lot of other stuff it does. I haven't given you much training on this, but I think there may be a link that you get with the material involved in this course that will bring you to the software on my personal webpage, and that also has its own tutorial documentation and detailed documentation of how to use the software if you're interested in actually using it. But I think I will wrap it up and open it up to questions at this point.
So thanks, Nicholas, for your excellent talk. This lecture, from your base of knowledge and depth of expertise, certainly benefited all of us. Now, may I request Professor Kayal for his remarks. Over to Professor Kayal.
Thank you, Santanu. Thank you so much. Yes, at the outset, I must say, Nicholas, it's incredible. Congratulations to you. And we have been enlightened really by this enlightening lecture.
Thanks.
I have just one small query. Suppose the largest aftershock, which is about, say, as you say, magnitude 1 down or so, if that largest aftershock occurs within 24 hours, how could this model help to really use this in a practical way? Could you please throw some light on this? When the aftershock, largest aftershock occurs within 24 hours, that we have observed in many cases. The aftershock, largest aftershock in case of Christchurch earthquake or in case of Nepal earthquake, really this model I think would really work, not a miraculous job. But for the largest aftershock within 24 hours, how could you use this model in a more practical way?
Yeah. Well, that speaks to the importance of having the generic model, the average model, based on past activity, because it's crucially important to get the aftershock forecast out as soon as possible. Because as I was saying, 50% of the aftershocks occur within the first day, that are going to happen within the first year, and that includes the largest aftershocks. So in many sequences, you really don't have time to think about it, do the calculations, decide on the models. It's really important to have something automatic, something set up where you can just plug in the location and the magnitude and get an estimate. Going forward, though, in those cases where you do have that largest aftershock within the first 24-hour window, that's also an indication that you have a slightly more, it could be an indication that you have a slightly more productive sequence than normal, if you do have a large aftershock in those first 24 hours. And so again, that's where the epidemic model is quite useful, where now you're considering not just the aftershocks of that main shock, but now you're considering also the aftershocks of that large aftershock. So I'd say, it's important to have a generic model ready to go before you have any information about the sequence, so you can give information about what's going to happen in that first day. And then you can use what actually happened in that first day to realize whether you're in a highly productive or a less productive sequence.
Thank you so much. I think you have time pressure, so I give it over to Dr. Santanu.
Yeah, thank you, sir. So now may I request Professor Ramesh Singh for his any remarks or any comments. Over to Professor Singh.
Thank you very much, Nicholas. It was very nice, and you are very close to us. I have a few questions to you. Like in the beginning, you showed the 6.4 or 6.2 in Japan, and after that, the main earthquake was occurred. So, did you try with your model? about the main event after seeing the 6.4 or 6.2 earthquake? And
Not, yeah.
yes, tell me.
Not for this sequence in particular. I haven't examined this sequence myself.
Okay.
Okay. We did have a similar sequence in California where it was a 6.4 main shock and a 7.1 aftershock, where we forecasts, and we did
in the Ridgecrest. Where?
So that was Ridgecrest, yes, and it was apparent even in the first day that this sequence was extraordinary. It had the productivity of an average 6.9 or 6.8. It was clear within the first day that we were in a very highly productive sequence. So it was not necessarily surprising that we had that subsequent main shock. This was a sequence where the probability that it was a foreshock was 2 to 4 times higher than average, and the forecasting model showed that was the case.
I see. And another thing is, we are sitting in so many small faults, and then you have a San Andreas fault. So there, suppose the earthquake occurred on one fault, a small fault, okay, and then do you account all the fault system there when you forecast about the aftershocks? Okay.
So in the statistical model that we're currently using at the USGS does not include information about where there are actually faults. We do have a model, you may or may not be familiar with it. It's called the USERF model, the Uniform California Earthquake Rupture Forecast. And we've built this epidemic type triggering into that model. That model includes the locations of faults and how long it's been since the previous earthquake. But unfortunately, we don't have validation of this model yet, so we're not using it in any operational sense. We're using it to kind of inform our own decisions behind the scenes, but we're a little ways away from being able to say with confidence how the presence of a large fault changes the probability of having a large earthquake. You know, my familiarity is mostly in California, and so far, all of the earthquakes that I've seen in California have been on faults that I didn't even know about. You know, the Ridgecrest earthquake happened on a fault system that was partially mapped. You could tell it was there after the fact, but the problem with using a model that assumes all of the earthquakes are going to happen on faults you know about is that you have to know about all the faults. So there's still a role for the pure statistical models until we can really be confident that we know where all of the potential faults are, and we know how the triggering relationships actually depend on your proximity to faults, which we don't know yet.
Very good. Okay, thank you very much. It was a very indeed interesting talk. Okay, and I see so many questions in your chat box, and maybe Santanu can take up and you may answer. So thanks a lot for your interesting talk.
Thank you.
So thank you, Professor Singh, and thank you, Nicholas. Now, may I request Ms. Antara to go for this question and answer session. Ms. Antara, over to you.
So I try to unmute. No, try to unmute your mic.
You have to unmute your speaker.
Is it raining?
Yeah, very raining too hot. Very raining too hot.
Lot of noise.
Oh, I see.
I think I can request Mr. Pliom, Mr. Prasidjo to go ahead. Mr. Prasidjo, for question and answer.
maybe 2 questions because Nicholas has got time pressure. Just 2 questions you select and ask the, you know.
Yeah, I'm happy to stay as long as necessary.
Okay, sir. There is a question from R. Arun Prasad. What is the foreshock and main shock magnitude size relation? How big is the main shock will be in terms of foreshock size?
Oh, that's a tough one. So the main shock size is very difficult to predict from the foreshock. It's that random distribution. So the most likely size of the earthquake is again smaller than the foreshock, but then you have this small chance of getting one larger. The most likely size for the earthquake larger than the foreshock is just marginally larger than the foreshock. So there's a larger foreshock. You might expect to have potential to trigger a larger main shock, but it's you can't say in any deterministic sense, because again it's that probability distribution where you have the main shock magnitude, and then the probability is getting lower and lower as a function of the triggered earthquake magnitude. So the most likely one is the same size, or the most likely one larger is just barely larger, and then it decreases in probability as you get larger. Unfortunately, we can't really say what the there's not information that we can use to say what the size of the impending main shock would be if that main shock happened, because we can't really identify sequences that are foreshock sequences from sequences that are not foreshock sequences kind of beforehand. All we can say is that each one has a certain probability of triggering something larger than itself, and then the probability of how large that earthquake is drops off exponentially with the magnitude of the triggered earthquake.
Thank you, sir. There is another question from Dipjyoti Goswami. Do you think laboratory acoustic emission and raised-state frictional experiment along with seismological data may provide critical insight in the understanding of earthquake precursory phenomena?
That's a great question. I've studied earthquakes in the lab for exactly that reason. And I think that the laboratory experiments suggested that there should be precursory changes. We always, laboratory failure is fairly easy to predict. But of course, the laboratory experiments are very well controlled. They're very homogeneous. The entire fault ruptures. There's none of the complexity and heterogeneity. But the laboratory experiments, especially on like intact samples, show these kind of distribution and coalescence of acoustic emissions, maybe far from the fault, getting close to the fault right before the earthquake. And I think what these laboratory experiments show is that, if I was looking for precursors, when you think about the scaling of those laboratory experiments compared to the Earth, I think the laboratory experiments are saying that we should be looking for precursors decades prior to the occurrence of those earthquakes. So I really think that's what we should take from those experiments. The acoustic emissions, I don't think there's a lot of promise that we're going to catch the nucleation of an earthquake, because nucleation occurs over such a small spatial area at such depth. But we might be seeing some of those larger scale effects where you have coalescence and localization of failure over the very long term. But that's going to be over decadal timescales, and not the timescales that we're worried about in the aftershock forecasting.
Thank you, sir. Should I proceed for more questions, sir?
Yeah.
Okay. Here's one from Anonymous. On July 5th, 2019, magnitude 6.4 event rocked Southern California, followed by another one, magnitude 7.1. Was the 7.1 earthquake a large aftershock?
Yes. Yes. So the magnitude 7.1, in the definition that we used, that was an aftershock larger than the main shock. And we say that it was an aftershock of the previous one because that you had that magnitude 6.4, which ruptured two faults actually, one to the southwest northeast and another one to the northwest southeast. And the 6.4 happened, and then there was a bunch of activity in this region, which then triggered off the magnitude 7.1, which then continued the rupture propagation in that northwest-southeast direction. So even though it was larger than the earthquake, we would consider it an aftershock because it was set off by that earlier earthquake. And this was that sequence where that earlier earthquake, that 6.4 that you talked about, was extremely productive. And we were able to see that over the first day, that this was a sequence that was much more likely, 2 or 3, maybe 4 times more likely than an average sequence to be a foreshock. So this is really a case where, you know, the statistical model gave us more information that this sequence was going to be a foreshock sequence. So if you define an aftershock as an earthquake that was triggered by an earlier earthquake, then the 7.1 is an aftershock. But if you're just talking about relative sizes, it was the biggest one in the sequence, so you would call it a main shock. But it was triggered, it was set off by the earlier earthquake.
Okay, sir. There's another one. Based on the present state-of-art research, can we use aftershock as a timely proxy to estimate the rupture area of a large earthquake? How many days of aftershock is suitable to estimate the rupture zone?
That's a really tough question. I don't have an easy answer for that one. I do think that aftershocks are a great estimate for the rupture area. In my science, I do use the early aftershocks as an estimate of the rupture area. But of course, stresses get transferred outside of the rupture area. So when you're trying to estimate the source distribution or the source extent, it's a little bit arbitrary where you draw the limit. But I would say, you know, the important thing to do to find the rupture extent is, in terms of this epidemic-type model, you can separate aftershocks into primary, secondary, tertiary, all of these different generations of aftershocks. And you can actually use the model to figure out, in a probabilistic sense, which of those aftershocks were actually caused by the first main shock. And so I think by using this epidemic-type model and looking only at the primary aftershocks of that first earthquake, then you can get a much better estimate of that initial rupture patch. But, you know, in terms of just a time horizon, you know, as time goes on, you get more and more secondary triggering, so you get better constraint on the initial rupture at early times. But it's hard to say. There are a lot of trade-offs, and I think what you would want to do is just maybe use that time decay function to weight the inclusion of those aftershocks. That's something I've done in the past to try to estimate rupture areas from early aftershocks. So kind of use that 1/time weighting. But it's non-unique. It's non-unique, the rupture extent you get from those aftershocks. But I still think it's one of our best ways to estimate what that rupture extent was.
Thank you, sir. There is another one. The physics of earthquake critically depends on the frictional properties of the fault zone materials, fault healing rate, effective normal stress, stiffness of the surrounding material, permeability, and many others. Have you incorporate all these parameters in your model?
Not at all. So I have studied those effects in the laboratory, but this goes back to, you know, we have a great physical understanding for how earthquakes work. When we're looking at friction in the lab, rate and state friction, permeability effects, pore pressure on the fault, healing since the last seismic cycle, we can measure all of these things in the lab. And we have a really good understanding for how friction evolves and strength evolves. But the thing is, for an actual earthquake that nucleates 12 kilometers underground, you don't have any idea what the conditions are. And I think some of our models, even for, you know, what the stress is 12 kilometers down, I think it might be a bit preliminary. You know, certainly when you're going, you know, toward the base of the seismogenic zone where you're getting the brittle ductile transition, I'm really not sure how to scale those laboratory measurements. So, I mean, there are a lot of people trying to bring in Coulomb rate state into the aftershock forecasting models, which is a good idea because, you know, you're relating to the occurrence of future aftershocks to kind of where the high aftershock activity is early on and where the stress was changed. I think that's probably a good productive avenue to pursue. But in terms of a lot of the details for what we know controls rupture initiation, I mean, unless we can drill down there and sample the fault on a centimeter scale, we could know the physics perfectly and still be unable to forecast the earthquakes based on those physics.
Yes, sir. There's a question from Dr. R. Arun Prasad related to dynamic triggering. Isn't it possible for a distant earthquake to affect the earthquake occurrence of another area at regional distance and keep them silent for a period of time? If yes, isn't necessary that they should be in a similar fault system?
So the question is whether dynamic triggering could cause a shutdown of seismicity, like the seismic waves could cause a decrease in seismicity?
Yes, sir.
I don't know. That's a very interesting question. I wonder if the person asking has looked at this, because during my PhD I was studying these remotely triggered earthquakes by seismic waves thousands of kilometers away from the first earthquake. And one of the things I did observe, usually you see nothing. Sometimes you see an increase in seismicity rate, but rarely you see a decrease in seismicity rate. And I never really understood it. But I think that I would expect that the passage, the dynamic triggering, our current understanding of faults is that the dynamic triggering should only cause an increase in the rate of earthquakes. So to cause a decrease is going to involve something that we don't yet understand about the frictional dynamics on that fault. But I do think that it's something that might exist in the observations. So all I can really say is that that's an important thing to look at in the future. And I do think that dynamic triggering and looking at how faults respond to those transient stresses of the seismic waves is one of our most powerful ways of conducting these natural experiments in the actual crust outside of the laboratory. I'm afraid that doesn't answer the question. It's a good one.
Yes, sir.
Ask whether you can ask any more question.
Should I proceed, sir?
You have time? You have some more time, or should we stop here? Okay.
So a couple more.
From Anup A. Sudhar, he wants to know, in epidemic model, how to distinguish between foreshock, aftershock, main shock in an earthquake catalog.
Well, it's just so with the epidemic model, that gives you a probability that a given earthquake was triggered by a previous earthquake. So that's separate from its magnitude. So it's just the time, it's the magnitude of the previous earthquake and the timing of the second one that determines how likely the second one was caused by the first one. And then the second one can have whatever magnitude it wants. So it could be larger, it could be smaller, it could be the same size. So the epidemic model gives you just the likely relationships, and it's all probabilistic. It's just the likely relationships between the earthquakes. And then the magnitudes themselves can be whatever they want. So the epidemic model really talks about earthquake rates going forward, and then the magnitudes affect future earthquakes. But there's not much the epidemic model can say about if there was anything different about an earthquake that ended up being larger than the previous one. It just doesn't have that backwards looking formulation built into it.
Yes, thank you, sir. An anonymous wants to know what conditions made a significant earthquake occur without aftershock or very low aftershock productivity. Like we often observe, intermediate earthquakes have only a few aftershocks.
Oh, intermediate depth, yeah. Yeah, there's a very strong depth dependence. That's one of the biggest signals that we see. Crustal earthquakes, the productivity tends to remain constant to about 12 kilometers, and then it drops off quite rapidly. So we had a magnitude 7 earthquake under Mexico City, which had 0 aftershocks. Magnitude 7 earthquake, 0 aftershocks, and we should be detecting aftershocks down to magnitude 3. And I think that just speaks to, you have the shallow crust where the properties are fairly, homogeneous, where you have brittle failure, but then anything below that, like in subducting slab, in the lower crust, you just have different mechanisms driving the slip there, or different kind of rheological conditions. In rate and state friction, we like to talk about the nucleation size. There's kind of a minimum size of an earthquake that will go seismically, and anything smaller will go quietly. So that's kind of our understanding of why those intermediate depth earthquakes have no aftershocks, is that things are just gooey. You have to have a really big brittle failure to actually generate, a dynamic slip pulse, and everything else just happens slowly. But then the real mystery is why you get an increase at even further depth as you go to a different mechanism for failure that involves phase transitions and maybe dewatering. I really don't know what causes those deep earthquakes, but that's the reduction in the number of aftershocks with depth makes a lot of sense with what we currently understand, and we can build that into our forecast models. The increase in triggering with further depth is a total mystery.
Yeah, thank you so much. I think we should stop here now. Let him be free. Yeah, thank you so much. Thank you so much. Yes, now
Yes,
over to
thank you. Yes. Thank you, Nicholas, for your kind presentation as well as for your question and answer session. Now, may I request Mr. Prasijjo for the vote of thanks. How about the Prasijjo?
Thank you, Dr. Santan sir. Good morning, respected dignitaries. I, on behalf of CSIR NIST and the entire organizing committee, provide the sincere gratitude to Dr. Nicholas Vander for such an informative talk and giving us insight about the aftershock forecasting. Thank you so much, sir, for sparing a valuable time from your busy schedule. Your lecture has showered tremendous knowledge upon us, and it was our honor to have you on board with us on this international workshop, sir. Now I deliver my sincere sense of gratitude to our respected director, sir, Professor G. Narahari Shastriji, for giving us the necessary permission to conduct this international virtual workshop. And my sincere gratitude goes to the chairperson of this session, Professor Jaya Kayal sir, and co-chairperson Dr. Saurabh Barua sir, for their continuous support and guidance, making this virtual workshop a success. Today we have here with us Professor Ramesh Singh sir from Chapman University. Sir, your presence has enlightened us. It was an honor to have you on board with us today, sir. Nevertheless, our sincere gratitude goes to the convener of this virtual workshop, Dr. Santanu Barua sir. Thank you so much, sir, for giving us this opportunity and platform to interact with such a prominent figures in the field of international seismology. And at last but not the least, we thank all the participants across the globe for their active participation, and the entire organizing committee for their tremendous effort and continuous hard work for making this international virtual workshop on global seismology and tectonics a big success. Thank you all. Love from India.
Thank you very much.
All right.